Okay, so this is chapter 14. We're going to start acids and bases. Today we're going to talk about the definition of acids and bases, acid and base strength, calculating pH and pOH, and probably up to calculating pH of strong acids and bases. You may want some additional scrap paper to take some notes. I've added some slides in here that I normally wouldn't add, but given our mixed group, I need to make sure that everybody knows what's going on. So let's begin. Definitions of acids and bases. So first of all, let's look at some properties of acids and bases. We know that acids have a sour taste. We also know that they react with various metals. So they react with various metals to produce hydrogen gas. They also react with carbonates. So I'm going to put CO3, 2-, and hydrogen carbonates, which would be your H2CO3, to produce CO2 gas. And that's really important. We've learned that in other units. They also react with a base in titration to produce, or neutralization, to produce a salt and water. They turn, they turn blue litmus red. So blue litmus to red. One thing that might be important for the AP exam is they also turn methyl orange red. It's like one of those weird indicator questions. They produce H plus as H3O plus in water. And H3O plus is simply a hydrogen ion attached to a water molecule. And they are electrolytes, meaning they have the ability to conduct an electric current. Let's look at bases. Bases have a bitter taste. They are sometimes characterized as slippery or soapy, meaning that slick feeling. They produce OH minus in water. I should have put over here, I'll do that in a minute. They have a pH greater than 7. They turn red litmus blue. Reacts with acid to produce salt and water. So titration. They are also electrolytes. Some examples: NaOH, which is lye. It's used in gardens. Potassium hydroxide, that's used in liquid soap. BaOH2, barium hydroxide, is used as a stabilizer in plastics. MgOH2 is MOM, milk of magnesia. Maybe some of you have taken it. And aluminum hydroxide is also another favorite friend found in Maalox. It's considered an antacid. Another thing, I think you already know this here, but I do want to add it in. Bases turn phenolphthalein pink. And I just want to go back to the other side for a second, and the pH is less than 7 over here. Okay, so let's talk about three different theories, acid-base theories. First of all, you have the Arrhenius theory, which is just the traditional theory. Traditional, I'm just going to abbreviate AB, acid-base theory. And basically all the Arrhenius acid is the acid produces H plus or H3O in solution. So for example, we have HCl plus water, and that produces H3O plus OH minus. Oops, not OH, sorry, Cl minus. H3O plus Cl minus. And simply bases produce OH minus as the only negative ion in solution. The only problem with this is not all bases contain OH. For example, you have NH3, which is a weak base. It is ammonia, and it can be mixed with water, but in solution it's going to form NH4 plus, which is the ammonium ion, and OH minus. So this produced OH minus in solution, but it didn't originally contain OH. The next theory is the Bronsted-Lowry theory, which tells us that acids are proton donors and bases are proton acceptors. When we talk about a proton, we're talking about a hydrogen atom minus electrons. So that's going to equal H plus, the hydrogen ion. An example here, we can do a couple. Let me see. We'll use the one that I did earlier, so the NH3 plus H2O yields NH4 plus OH minus. So here, when we look at this example, the H2O is donating to NH3. So this is considered the acid, and this is considered the base because it's accepting the proton. I'm going to introduce a new term here. So if this is the base, this is considered the conjugate acid, and this is considered the conjugate base. And I'll explain that in another slide here. One other quick example of this, and you don't have to write this one down if you don't want to. We have HCO3 minus plus H2O yields H3O plus CO3 2 minus. So this is interesting in the sense that now you can see that the HCO3 is donating, so this is the acid, and the H2O is the base because it's accepting. So the H3O is my conjugate acid, my Ca, and the CO3 minus is my conjugate base. So that's going to lead us to a very interesting discussion, in the sense that a little bit later on you'll see that water is something that's considered amphoteric, which means that it can act as an acid or a base. And the last one, before I explain to you a little bit more about conjugate acid-base theory, is the Lewis theory of acid and bases developed by G.N. Lewis. And this is just another general model for acid-base behavior. He defined an acid as an electron pair acceptor, and a base is an electron pair donor. And the reason why this is an electron pair acceptor is because it has an empty orbital to accept a lone pair from another molecule. And the reason why a base is an electron pair donor is because it has a lone pair to donate. Very simple. So let's look at an example here. If I have H plus, and let's take the molecule NH3. So I'm going to draw it like this so you can see it. Here's NH3. And that's going to yield NH4 plus. And as you can see here, the Lewis base in this case was the NH3 because it had a lone pair to give, and the H plus was the Lewis acid. Okay, so basically this table sums up the three theories: Arrhenius, H producer; OH minus producer; Bronsted-Lowry, H donor; base, H acceptor; Lewis acid, electron pair acceptor; base, electron pair donor. Let's talk about conjugate acid-base pairs. Conjugate acid-base pair is two substances related to one another via donating or accepting a single proton. Via donating, accepting a single proton. So, for example, if I were to demonstrate an acid, so we're going to just call this HA. A is for acid, it's just a generic acid, I'm not naming a specific one, plus water yields H3O plus aqueous and A minus because it's been stripped of its proton. So here you can see that HA is donating to H2O. So this is considered my Bronsted-Lowry. So this is my acid donating. This is my base. Remember, conjugate acid-base pair are two substances related to one another via donating, accepting a single proton. So this donated the proton, this lost it, so this is my conjugate base. And H3O gained the proton, so this is my conjugate acid. If I were to do this with a base, let's look at, we'll just do this as B, here's my base, plus H2O yields HB positive aqueous plus OH minus. This is my liquid. So this is, sorry, this is aqueous. This is liquid. Aqueous. So here, H2O donated, right, to B. So this is my HB. So this is my acid. This is my base, which makes this my conjugate. This is the base, this is the conjugate acid. This is my acid, this is my conjugate base. Okay, moving on. Acid dissociation constant. Let's change color here. So this is just like anything else that we've been doing, okay? We are going to use Ka values, just like we did in the equilibrium unit. So Ka is going to be equal to the concentration of the products over reactants. So for my Ka, using the example that I just did with HA plus H2O yields H3O plus an A minus, what I would have is my Ka is equal to my H3O plus times the concentration of my A minus over the concentration of HA. And my Kb would be the concentration of the products over the reactants as well. I'm not going to rewrite that, but using the example that I just did with base plus water yields Hb plus OH minus, my Kb would be equal to the concentration of H3O plus, oops, my Kb would be equal to the concentration of Hb plus times the concentration of OH minus over the concentration of B. Please remember again that no liquids or solids in Ka expressions. In K expressions. And that's from the last unit. These are some values for Ka for some common monoprotic acids. There's also a list in the back of the book that has all of them. So I just want to look at a couple of examples. These aren't in your note packet, but just listen to this and it'll make sense. It says, write the Bronsted-Lowry dissociation reaction for the following. Identify the Bronsted-Lowry acid and base along with the conjugate acid and base. Determine the conjugate acid-base pairs. State the equilibrium expression for the dissociation reaction. So we have acetic acid. Okay, so here's acetic acid, sometimes written as HC2H3O2. This, my source is old school. So we have that plus my base. And why is my water my base? Because as you can see here, the H3, the acid is donating an H to the H2O. So that's my acid, it's donating. This is my base, it's accepting. So this becomes my conjugate acid, and this is my conjugate base. So here's my conjugate acid-base pairs, the CH3COOH and the CH3COO minus without the H, and then the H2O. So again, the only difference is the proton, and then I write my expression, products over reactants. Here's an example of a base, the cyanide ion, Cn minus plus H2O yields HCN plus OH minus. You can see here that the water donated to the Cn minus, so the water is acting as my acid, and then my acid-base pairs, and then my expression. Okay, relative strength of acids and conjugate bases. This should make sense to you. The stronger the acid, the bigger the Ka value. So the stronger the acid, the weaker its conjugate base. So that's important. And I think I have that on the next page. The weaker the acid, the smaller the Ka value, the stronger its conjugate base. So order the following acids from strongest to weakest. So you would have to look up the Ka values here. The one that has the bigger Ka value is going to be the strongest. So if we were to look at this, HClO4 is actually the strongest because they don't even have a Ka value. It's so strong it says very large. And then followed by H2SO3 with 1.5 times 10 to the negative 2, followed by HF 7.2 times 10 to the negative 4, and HNO2 4 times 10 to the negative 4. Okay, this should make sense to you because HNO2 is one of our strong acids. We know H2SO4 is a strong acid, so this is not H2SO4, but it's not, this is actually considered weak, but it's got 2 protons compared to these two that have 1 proton, and we know HClO4 is still considered fairly strong, but HF is definitely weak. Let's look at it for some bases. So the same thing, the higher the Kb, the stronger the base. So if we were to look at these Kb's, what we would find is Cn minus. Well, they looked at the Ka values of HCN. So HCN, so Cn is a conjugate base that came from HCN. I probably should write this down because it might not be that clear. SO4 2 minus came from SO4, HCl, and this came from acetic acid. This actually should be H2. Yeah, I think this has got to be H2SO4. If this is 2 minus, I think this is a typo down here. So when you look up the Ka values, get 6.2 times 10 to the negative 10, 1.8 times 10 to the negative 5, 1.2. So we're going from, remember, strong acids have a weak base. So we're going from the strongest base to the weakest base, which means that we're going from the weakest acid to the strongest acid. And that's what they did here. If we were to write the dissociation reaction for the following monoprotic acids. So they want you to write the dissociation reaction. So this is HI in water, and it's simply going to H3O to I minus. See, this is a direct arrow because HI is very strong, so Ka is very large. It's going to ionize 100%. Where acetic acid is a weak acid, it's going to barely ionize, which I'll talk about on the next page. We need a double arrow because this is going to keep going back and forth. And because it's a very weak acid, the Ka is going to be extremely, extremely small, a lot less than 1. I want to just talk a minute about diprotic acids. This isn't really for the first half of this lesson, but I don't really spend any time talking about diprotic acids. We talk about polyprotic acids in the next lesson. But a diprotic acid or a polyprotic acid is simply an acid that's got more than one H. So a diprotic acid has 2 H's that it can donate. A triprotic acid has 3. And this has to happen in stepwise. So if you have your original diprotic acid in the presence of water, what's going to happen is 1 H is going to come off first and give you HA minus. and this would be your Ka1. Then in the next step, okay, you would take the conjugate base that was produced as a result of the first dissociation and in water. Now the second H comes off and you have A2 minus, and then your Ka2. If you had a triprotic acid, it would be a third dissociation. And what we'll find as we go along is that as the subsequent H's are removed, it really doesn't affect the overall concentration or pH of the resulting solution. It's really the first one that does all the all the work, and you'll see that as we get to polyprotic acids and we do some calculations with them. So in these two examples, you have H2SO4, and you see the one H is removed. It's direct arrow because it's very strong. And then when the subsequent H comes off, you see we have a double arrow because now HSO4 minus is considered weak. So the equilibrium is going to go back and forth, back and forth. And you can see that the Ka2 value is very small. So when I said that the subsequent Ka values really don't affect the ending solution, you can see why. Here you have an acid, and it's very, very weak to begin with, so you have a double arrow. You remove one H, and then you remove the second H, still a double arrow. So both your Ka1 and your Ka2 are very, very small, which means that they don't really dissociate in water. So when we talk about what's going to be the major contributor of H ions in solution, it'll be the water and not really the weak acid. So that brings us to our next discussion on acid strength. Okay, so strong acids, we just said that the Ka will be very large. The acid completely ionizes. And the equilibrium lies to the right. Equilibrium lies to the right. And when you have a strong acid, you have a weak conjugate base. Now, you have a diagram in your notes that shows you before dissociation, you've got like HA here, and then after dissociation, you have the same amount of H plus and A minus. And that's because this is a complete, and you can write this in your graph, dissociation. I want to give you a little bit more notes here, so this is really driven home strong. So with the strong acid at equilibrium, what do we know? We know that the concentration of the acid is approximately 0 because it completely dissociated. So what we also know is that the concentration of our H3O plus is approximately equal to the A minus, which is approximately equal to whatever the HA was initially. And I can draw these conclusions just based on looking at that little graph. So what else do I know? I know that my Ka, as I said, is much greater than 1. So Ka is much greater than 1, very large. And if I were to write a Ka expression, it would simply be the concentration of H3O plus times the concentration of A minus. Normally we would put that over HA. However, we know that this reaction completely ionizes, so this is really 0 molarity. Now, what would this look like in an ice table? And yes, I know I'm not giving you an example yet, but this is important that you understand this because this is what we're going to actually be doing with these acids and bases. So I have my HA plus my H2O yields H3O plus A minus. Remember that water is a liquid, so it has no business in the ice table. So if I were to look at this, I have some initial concentration at the start of the reaction, and I don't have any of this. And as the reaction proceeds, this becomes minus X plus X plus X. At equilibrium, this is going to be 0 because it completely ionized, and this is going to be X and X. Let's look at weak acids. So this barely dissociates. And we're talking less than 5% dissociation. So mostly the solution stays as HA. Your equilibrium is going to lie to the left. And if I were going to represent this kind of similarly like I did over here, what we know about a weak acid at equilibrium is that the HA, the original concentration of the acid, is greater than the H3O plus. Or what we can say is that the HA is still equal to, or approximately, make that approximately equal to whatever the HA was initially. Your Ka is less than 1. And if I were to write an ice table for this, I have HA plus H2O Now, even though, I'm going to explain this, even though we write this as if it dissociates, what we really know is that this is a left arrow. Okay, the equilibrium lies to the left because this isn't going to dissociate, because this is a weak acid. This is considered my base. Remember, this is considered my conjugate acid. This is my conjugate base. So if I'm looking at an ice table, I'm starting with some known concentration. This is 0, this is 0. This is going to be, we're going to use another variable. This is going to be minus y. This is going to be very, very little. This is going to be plus y. This is going to be plus y. So what we know is that equilibrium, that x minus y is approximately equal to x. There's nothing here because this was my water. And this is simply going to be y. And what can be said is that y right here, oops, I forgot to write x minus y there, sorry. Y right here is much less than x. That's why at equilibrium, x minus y is approximately x. Okay, some strong acids. You need to know these. HCl, HBr, we went over these at the beginning of the year. HI, HClO4, HNO3, and H2SO4. And there are two others. If you HClO3 is considered pretty strong, and HI. I don't see them on the Regents of the AP exam too much. This one I do see from time to time. I don't usually see that one. Okay, let's talk about bases. What do we know about bases? So we know that the Kb is much greater than 1 for a strong base. We know that it's going to, just like an acid, dissociate completely. We also know that our strong bases are usually hydroxides of group 1 and some group 2. They're called dibasic. And they don't really dissolve well though in water, even though they're strong. And those are your antacids that I was mentioning earlier on the first page. A weak base, the Kb is going to be less than 1. They usually contain nitrogen. So some examples here would be NH3, NaHCO3, and Na2SO3. I'm not going to worry about amines right now. We're going to just table this for now. All right. A list of bases. This should say list of, I don't know why this should say list of strong bases. As I said, most of your group 1, so you have your LiOH, your NaOH, your KOH, your RbOH, and your CSOH. From group 2, the ones that I would really know are just basically MgOH2, CaOH2, perhaps barium. I think that's about it for right now. Okay, let's talk about the pH scale. Just listen to this right now. This should make sense to you. This is a little bit of Regents Chem review. We know the pH scale is a logarithmic scale to measure the acidity of the relative hydronium ion of a solution, hydronium concentration. The lower the pH, the more acidic. We know that, less than 7, meaning less basic, which means if it's more acidic, there's more H3O plus than OH minus. And the higher the pH, the more basic, so greater than 7, meaning less acidic. So that means that your OH concentration is going to be greater than your hydronium concentration. Acidity is not the same as acid strength. Just because a solution has a low pH, it does not mean that it is a strong acid. So highly acidic does not equal strong acid. We usually measure it between 0 and 14, 7 being neutral, but it can be above 14, meaning extremely basic, or some of our really strong acids have a pH less than 0. This you should remember from Regents Chem. An increase of 1 on a pH scale means a decrease of hydronium concentration by a factor of 10. An increase of 2 on the pH scale means a decrease of hydronium ion concentration by a factor of 100. So everything is a tenfold increase or decrease. So if I say that I have a pH of equal to 3 and the hydronium ion concentration increases 100 times, then my new pH is equal to 1, because 10 times 10 is 100. So there was a change of 2 pH value, and this increased, which means that it's getting, stronger. On the pOH scale, the logarithmic scale to measure the acidity or relative OH of a concentration in a solution, the lower the pOH, the more basic it is, meaning it has more OH, less hydronium. The higher the pOH, the less basic, meaning more acidic, which means that the H3O hydronium concentration exceeds the OH minus concentration. Again, basicity is not the same as base strength. Just because a solution has a low pOH, it does not mean that it is a strong base. Again, an increase of 1 on the pOH scale means a decrease of OH minus by a factor of 10. So it's the same thing that I was just talking about, but in this time we're talking about pOH. Okay, so let's get into our notes. So autoionization of water. As I told you earlier, water is amphoteric. So it can act as either an acid or a base. It can act as either an acid or a base. And water autoionizes. What that means is it can transfer a proton from one water molecule to another. So transfer of a proton So if I were to give you an example of this, it would kind of look like this. You have H2O plus H2O and that's going to yield H3O plus OH minus. And this can also happen with NH3, where you have NH3 plus NH3 yields NH4 plus NH2 minus. So what we have to remember is that water is neutral. Water is neutral. So the Kw for water is simply the H plus concentration times the OH minus concentration, which is going to equal 1 times 10 to the negative 7 times 1 times 10 to the negative 7, which is going to equal 1 times 10 to the negative 14, which is how we get our overall scale of 14. If I were to write the Kw for water, it would look like this, where you would have H3O plus OH minus, which is what I just did, over H2O. Oops, sorry. Over H plus. Okay, which also equals oops, I'm sorry. If I were to write the Kw for water, it would simply be the concentration of H3O plus times OH minus, because pure water, liquid, is not put into the expression. Therefore, we know that the H3O concentration is equal to the OH minus concentration, as we said, which is equal to 1 times 10 to the minus 7, which is how we arrived at that up there. All right, let's look at definitions. pH is the negative log of the H plus concentration, and POH is the negative log of the OH minus concentration. So for example, if I tell you that the H concentration is equal to 1 times 10 to the negative 10, in my calculator I do negative log of 1 times 10 to the negative 10, and I get a pH equal to 10. And I do the same thing for POH. The pH plus the POH equals 14, which should make sense. And 10, so basically the antilog, so 10 to the minus pH is going to equal our H plus concentration, and this should say 10 to the minus POH equals our OH minus concentration. Okay, before I have you do the table that you have next on your sheet, I'm going to go through a couple of examples of this to make sure that you really know what you're doing. Here's the first example: calculate the pH and the POH for the following solutions. So if I have 0.01 molarity HI, we know that HI is a strong acid. It's going to completely dissociate, notice the one-way arrow, into H3O and I minus. So we know that our HI initial is really equal to our H3O. So pH is equal to the negative log of the hydronium concentration. So negative log of 0.01 gives me a pH of 2. My POH is simply 14 minus 2, which gives me a POH of 12. In B, I have another strong acid. I have 5 times 10 to the negative 6 molar HClO4. Completely dissociates, noted by the strong arrow. So my pH is the negative log of the H concentration, which gives me a pH of 5.3, and my POH is 14 minus that, which is 8.7. Now going the other way, well, here's some examples of bases. 1.5 molar KOH is a strong base, completely dissociates. So we have the negative log of the OH minus concentration, which gives us a POH of negative 0.176. So then our pH is 14 minus my POH, which gives me a pH of 14.176. So this is an extremely, extremely strong base. BaOH2 is also a strong base, dissociates as you see here. So we know the OH minus concentration is equal to 2 times the concentration of BaOH2. So it's going to be 2 times 10 to the minus 3. And that's simply because it was a dibasic, okay, or dihydroxy base. So we have negative log of the OH minus concentration. So negative log of 2 times 10 to the minus 3 gives us a pOH of 2.7. So 14 minus 2.7 gives us a pH of 11.3. So these were all examples of finding pH and pOH. Now I'm going to do a couple of examples of finding the concentration from the pH and the pOH, and then I'm going to let you play in the table. So here you're asked to calculate the hydronium concentration and the hydroxide concentration from the following solutions. So if I have a pH of 4, remember that my pH is equal to the negative log of my hydronium concentration. Therefore, my pOH is equal to 14 minus my pH. So my hydronium concentration is equal to the anti-log of the negative pOH. So the anti-log of the negative pOH gives me a concentration of 1 times 10 to the negative 10. In this example, pOH is equal to 3. So remember that to find my pH, it's 14 minus my pOH, which gives me 3. So therefore, it would be the anti-log of the negative pH. So anti-log negative 11 gives me a hydronium concentration of 1 times 10 to the negative 11. And you can look at these other examples if you want, and then continue. So here's our table. So if my pH is 2.3, then my pOH has to be 14 minus PO3, my pH, which is going to be 11.7. My hydronium concentration. Remember that if I have my pH, to get my H concentration, I have to do the anti-log of the negative pH. So this is going to give me, in your calculator, you're going to do anti-log of negative 2.3, which gives you 0.005. I want you to pause me right now, try to fill in the table, and then come back and check your work. And hopefully I didn't make any mistakes. This table kind of sums up everything about how you're going from H concentration to pH, or pH to H concentration, pH to pOH, and vice versa, and then my pOH to my OH minus, and my OH minus to my pH, and then also between the H plus and the OH minus. So here you can see if I'm going from OH minus to H, it's 1 times 10 to the 14 minus the concentration, divided by the concentration of OH minus. And if I'm going from H plus to OH minus, it's 1 times 10 to the minus 14 divided by the H concentration. Okay, some solving acid-base problem criteria. You need to list the major species in solution, look for reactions that can be assumed to go to completion, meaning strong acids or strong bases. For a reaction that can be assumed to go to completion, you need to determine the concentration of the products, write down the major species in solution after the reaction, look at each component, decide if you're dealing with an acid or base. Pick the equilibrium that will control the pH, use the known values of the dissociation constants, write the equation, use an ICE table, define X, determine X, and substitute the concentrations back into the equilibrium expression to solve for X. and then check for the validity of approximation. So that's the 5% rule that we did in the last unit. And then calculate pH and any other concentrations. Now we're not going to really get into this today. We're just going to do a couple sample problems, very basic. That's really for the next lesson. But these are the set of rules that you need to be following. So calculating the pH of strong acids or bases. So what you know about a nitric acid solution, you know that it is a strong acid. You know that the major species so we have H plus, we have NO3 minus, and we have H2O. And because we have basically 100% ionization, really the water can be neglected, because even though it auto-ionizes, it will be minimal compared to what's going on with the HNO3. So basically we can conclude that our sources of H plus are from HNO3 and, as I said, H2O, but this one is really going to be irrelevant compared to the HNO3. You want the ones that are going to contribute the most. So if I have an H plus concentration equal to 0.10 molar, then my pH is equal to the negative log of 0.1, which is going to equal 1. Here we have calculate the pH of a 1 times 10 to the negative 10 molar HClO4 solution. And what we can conclude here is that since the concentration of HClO4 is so small, it really will have no effect on what's going on, and that the H2O is the major source of H plus. And since we know that the concentration of H plus in water is equal to 1 times 10 to the negative 7, then the pH is simply going to be equal to 7. In this next example, you're adding 2 strong acids. So you've got nitric acid with a molarity and volume and HCl with a molarity and volume, and they want to know what the resulting solution is. In this type of problem, you want to get the total millimoles and you want to divide it by total volume. So what we know here, let's look at dissociation. We have HNO3 dissociating into H plus NO3 minus, and this is going to be a very large Ka. You've got HCl dissociating into H plus Cl minus, which is also going to be a very, very large Ka. And then you have H2O dissociating into H plus and OH minus. And here you know that the Kw is equal to 1 times 10 to the minus 7. Now, honestly, these are so strong that this is going to be minimal and can be neglected. So what we need to do is we need to take HNO3 first. Remember that if we take the molarity, so we've got 0.00125 molarity times the milliliters is going to give us millimoles, which gives us 0.0675 millimoles. Anytime we take molarity times milliliters, we get millimoles. And then we have HCl with a molarity of 0.025 times 25 milliliters equals 0.625 millimoles. Which gives us a total, grand total of 0.06925 millimoles divided by the total volume, which is 54 and 25, which is going to give us 79 milliliters. And that's going to give us a molarity equal to 0.088 molar. And remember that your pH is equal to the negative log of your H concentration. So negative log of 0.088 is going to give us a pH equal to 2.06. And in the last example, what is the pH of a 25 milliliter of 0.25 molar solution of NaOH? NaOH is a strong base. Okay, so Na plus OH minus. So in a strong base, you're just going to do your POH is equal to the negative log of the OH minus concentration. So our POH, so it's the negative log of 0.25, gives us a POH equal to 0.6. And remember that your pH is going to be equal to, well, let me preface that by saying your pH plus your POH equals 14. So therefore, your POH is equal to 14 minus your POH, which is going to give you a pH equal to 13.4. Okay, that's it. Have a great day.